Hello everyone. On this video we will be covering double integrals and polar coordinates. Okay, so before we get started, we're going to do a quick reminder that for polar coordinates, you would use x equals r cosine theta, y equals r sine of theta, r squared equals x squared plus y squared, and tangent of theta is equal to y over x. Okay, so the region that we usually use our x and y for, so where a is between, well, x is between a and b, and y is between some value c and d, will now become our region is equal to some r theta, such that r is between two other r values, and same with theta. Theta is between two different theta values. Okay, which brings us to our change of variable in polar form. Well, two polar forms. So change of variables to polar form. Okay, so what if we let R represent our region? So the plane consisting of all points x, y, which is of course equal to r cosine theta, r sine theta. Okay, satisfying the conditions. Where our theta function, well, our first theta function is less than our second theta function. Oh, got my 2 there. So they're between 0 and the first function. Okay, so r is between our two theta functions. Our theta is between, we'll call them alpha and beta instead of theta number 1 and theta number 2. And that's where theta is between 0 and 2 pi. Well, the distance between the alpha and beta is between 0 and 2 pi. Okay, so we're not going around over and over and over again. Okay, so as long as our first and second theta functions are continuous, so in other words, if g1 and g2 are continuous on our interval, and our function is continuous over our region, Okay, so that means our double integral over our region is going to be equal to the integral from some alpha to beta and some integral for our first theta function to our second theta function is f of r cosine of theta, r sine of theta, times r, and that's dr d theta. Okay, so if you are going to use the polar form, that's how it would look. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and start on our first example. Okay, so let's say for our first example, we want to evaluate the double integral of sine theta with respect to the area of the region. Okay, now normally this would be pretty simple. You just go ahead and do the double integral, but whenever you have certain regions, that's when it kind of gets a little more complicated. So where your region, where R is the region, in the, give that a little more space, in the first quadrant, that is outside the circle, R equals 2, and inside the cardioid, R equals 2 times 1 plus cosine of theta. Okay. Now, if you are unsure of how to sketch a polar function, feel free to go back and look at the video I have on how to sketch those. But for this problem, it's usually easier to visualize what you have to do if you sketch both of those on the same graph. Or if you have a graphing calculator, you know how to use that, you're more than welcome to sketch both of those on the graphing calculator. Okay, so sketching the two polar functions. Gives, so if we're going to go ahead and sketch that, that's our axis there, and r equals 2 is literally just a radius of 2. Okay, so this is your r equals 2. And your graph of, let me see, kind of looks like that. This is the function r is equal to 2 times 1 plus cosine of theta. Let me clean up that theta a little bit. Okay. Now the region in the first quadrant outside of r equals 2 and inside our cardioid is actually this section here. Okay, so the two things that this tells us, that as soon as you see first quadrant, we know that our theta is between 0 and pi over 2. Okay, so now we just have to find our actual theta functions. So we know for our theta functions, we have zeros less than or equal to our first theta function, less than or equal to r, less than or equal to our second theta function. Okay, well, in this case, our theta function is 2 and 2 times 1 plus cosine of theta. And we really don't need the less than or equal to 0, because we know that 2 is not going to equal 0, so we don't really need it. Alright, so now that we have our boundaries, we can go ahead and start working out our problem. So bring that up just a little bit more. Try to save some space. Okay. So our double integral of sine of theta will end up being the integral from 0 to 2, and the integral from, remember that's r equals 2 to r equals 2 times 1 plus cosine of theta. And that's sine of theta. Remember, it was also times r in our formula. That's dr d theta. If you want, you can put the r in front, or you can leave it right there. Completely up to you. Okay, so as always, we're going to integrate from the inside out. Okay, so we have our integral from 0 to 2. Oh, 0 to pi over 2, my mistake. I don't know why I put 0 to 2. Glad I caught that, because that would not have made much sense. Pi over 2 to pi over 2. There we go. Okay, so if we integrate with respect to r, that just becomes r squared over 2. So we have, I'll just move that out to the front, r squared over 2 sine of theta. And that's from 2 to 2 times 1 plus cosine of theta. And of course, our d theta just follows us. Alright, so that actually brings us to, from 0 to pi over 2, we plug that in, that's 2 times 1 plus cosine theta squared, okay, which ends up being 4 times 1 plus cosine theta squared over 2. And that's times sine of theta, minus, plug in 2, you have 2 squared, which is 4. So you have 4 over 2 sine of theta. That's d theta. Okay, so you have 4 over 2, 4 over 2, so you have 2 in both of these, so actually you can just factor that right on out. So you have 2, from 0 to pi over 2, of 1 plus cosine theta squared sine of theta minus sine of theta with respect to theta. Okay. Now for this first term, we can go ahead and use u substitution. We integrate that. So just a quick little hint. So if we made u equals 1 plus cosine of theta, and our du is equal to negative sine of theta d theta. we'll actually end up with 2 times negative 1/3, 1 plus cosine theta to the third power, and the integral of sine of theta is negative cosine of theta, so that's plus cosine of theta, from 0 to pi over 2. Alright, now if we go ahead and plug in our pi over 2, it's 2 times cosine of pi over 2. Remember, cosine of pi over 2 is just 0, so we end up with negative 1/3 times 1, which is just negative 1/3. We plug in 0, we end up with cosine of 0 is 1. Oh, actually jumping ahead because cosine over there, that actually gives us 0. Except jumping ahead a little bit. There we go. So now plugging in the 0, we get cosine of 0, which is 1. So we have 1 plus 1 is 2. So we have negative 1/3 times 2 to the third power plus 1. There we go. And all of that times 2. Okay, so we end up with 2 times negative 1/3 plus 8 over 3 minus, once we distribute that, minus 1, or we can make that minus 3 over 3, which is equal to 2 times 4 over 3, which is 8 over 3. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so let's say for this example, what if we let R be the annular region, and annular is just a fancy way to say ring shape. Line between two circles say x squared plus y squared equals 1, and x squared plus y squared equals 5. Okay, what if we want to evaluate the integral? And the integral is double integral of x squared plus y with respect to the area of the region. Alright. Now once again, it looks like they didn't really give us enough to work with. It looks like they left out a bunch of stuff. They really didn't leave out a bunch of stuff. You just have to know how to find it, where to look. Okay, so if you remember, that x squared plus y squared equals r squared. Okay, so that means the polar boundaries for, we have x squared plus y squared, we can make that 1 squared. X squared plus y squared equals 1 squared, and x squared plus y squared equals 5, we can make that square root of 5 squared. Same as 5. Okay, so we can make our r, since it's just r squared, between 1 and square root of 5. So 1 and square root of 5. And since we know it's annular or ring shaped, we know it's going to be between 0 and 2 pi. Or theta, rather. Okay, it didn't say quadrant 1 or quadrant 2 or the top half or the bottom. It said the annular region, so we know it's the entire, between the entire circle. Okay, so once again, everything we need is there. We just have to know how to find it, how to pull it out. Okay, so now that we have our boundaries, we can start solving. Okay, so the region of x squared plus y, yay, is equal to, let's say, from 0 to 2 pi, and from 1 to square root of 5, or r equals, if you want to do that, make sure you don't make any errors. And instead of x squared, remember x is equal to r cosine of theta. So we can make that r cosine of theta squared, or just r squared cosine squared theta. X equals r cosine of theta, y equals r sine of theta. Just a little reminder there. Okay, plus y, so let's plus r sine of theta. Remember, you have to multiply that by r. Okay, you can't just replace those when you're doing polar functions or polar coordinates. You have to remember that r, and that's dr d theta. I hate to see you go through all the work and realize you messed up towards the beginning by leaving out that r. Alright, so just like always, we're going to integrate from the middle out. So the first thing we're going to do is go ahead and distribute that r. So that's the integral from 0 to 2 pi. R equals 1 to square root of 5. That's going to be r to the third cosine squared plus r squared sine theta. And that's dr d theta. Alright. So if we go ahead and integrate this with respect to r, that's just r to the fourth over 4. That's the integral from 0 to 2 pi. R to the fourth over 4 cosine squared theta plus r to the third over 3 sine theta. And that is from 1 to square root of 5. Alright. Now we're going to plug in our square root of 5. 0, oh, forgot my d theta. Okay, so from 0 to 2 pi. We plug in our square root of 5. You know, square root of 5 times square root of 5 is 5. So if we go square root of 5 to the fourth power, that's 5 times 5, which is 25. So we have 25 over 4 cosine squared theta plus 5 square root of 5 over 3 sine of theta minus, we plug in our 1, so we have 1/4 cosine squared plus 1/3 sine theta. And that's with respect to theta. Okay, so We go ahead and combine our like terms. If you combine those two, you have 25 over 4 minus 1 over 4, which is 24 over 4, which is just 6. So that leaves us 6 cosine squared theta plus 5 square root of 5, and that's minus 1. So you have 5 square root of 5 minus 1 over 3 sine of theta, and that's with respect to theta. Alright. Now, remember your trig identities. You know that 6 cosine squared of theta. We can make that a little bit bigger. We can make that 3 times 2 cosine squared theta. Okay, which we can make 2 cosine squared of theta is just 1 plus cosine 2 theta. 1 plus cosine 2 theta using our trig identity. Okay, so this is just 3 times 1 plus cosine 2 theta. We distribute that 3. We will end up with, from 0 to 2 pi, 3 plus 3 cosine 2 theta plus 5 square root of 5 minus 1 over 3 sine of theta with respect to theta. Yep, the little trig identities come in handy. Okay, so if we integrate each section, or each term, we have 3 theta plus cosine of 2 theta is sine of 2 theta over 1/2, so that's, well, over 2, which is 3 over 2 sine of 2 theta, minus 5 square root of 5 minus 1 over 3. Integral of sine is negative cosine, so that's why the sign changed. Cosine of theta, and that's from 0 to 2 pi. Okay, so if we go ahead and plug in our 2 pi, we have 6 pi plus sine of 2 times 2 pi is sine of 4 pi, which is 0. So 6 pi plus 0. Oh, forgot my... minus 5 square root of 5 minus 1 over 3 times cosine of 2 pi, which is just 1, minus, plug in 0 here, you get 0. Plug in 0 here, you get 0. Plug in 0 here, you get 1. So that's minus 5 square root of 5 minus 1 over 3. Okay, so this is minus. If you distribute that, you get plus. So these two actually cancel out. So you end up with an answer of 6 pi. Excuse me. Alright, so if you are still writing, feel free to press pause. But we're going to go ahead and do one more example. Alright, so let's say, for example, if we want to use the double integral to find the area enclosed by the graph r equals 3 cosine of 3 theta. Okay, so in this case, it's another case of drawing the graph helps a lot, because this is literally all they give you. So drawing the graph will definitely help. So in this case, it is helpful to draw the graph. Okay. And once you draw the graph, again, if you are a little rusty on graphing polar functions, I do have a video on that. Okay, so you have 3 petals, and they're all the same size, so forgive me if I'm a little bit off, but they should be the same size. Okay, and this one petal, you can actually get that one petal between theta is negative pi over 6 and pi over 6. Okay, so if all 3 are the same size, you can just find the area of one petal and just multiply it by 3. Okay, so if we can find the area of this one petal, we're good. Okay. So one petal is bounded by negative pi over 6 and pi over 6. Okay. And we know that our radius is between 0 and 3 cosine of 3 theta, because you have to start at radius of 0. That's right there at the beginning. 3 cosine of 3 theta. Okay, so we have our boundaries. Okay, so if we find the area of one petal, okay, so that's going to give us the integral from negative pi over 6 to pi over 6, and the integral from 0 to 3 cosine of theta. That's from r dr d theta. Okay, now if you like, you can plug that in, but honestly, it's simpler to just solve it as r. Okay, because if we integrate with respect to r, it's just r squared over 2. Okay, so from negative pi over 6, pi over 6, we have r squared over 2 from r equals 0 to r equals 3 cosine theta. Okay, and of course that's our d theta. So if we plug that in, well, so if we plug in 0, we get 0, so it's just going to be, move that over a little bit, the integral from negative pi over 6 to pi over 6 of 3 cosine theta squared is just 3 squared and cosine squared, so that's 9 over 2 cosine squared. So we're going to just pull the 9 over 2 on out now. So we have cosine squared theta, well, cosine squared 3 theta, sorry about that. There we go. That's d theta. Okay, now, again, from our trig identities, we have cosine squared of u is equal to 1 plus cosine 2u over 2. Okay, so that means this is going to be cosine squared of 3 theta is equal to 1 plus cosine 2 times 3 theta, which is 6 theta over 2. So if we go ahead and bring that 2 right on out front here, that's just going to be 9 over 4 from negative pi over 6 to pi over 6, 1 plus cosine of 6 theta. D theta. Okay, so if we go ahead and integrate both of those terms, we end up with 9 over 4, and rho of 1 is just theta, plus, that's going to be 1 over 6 times sine of 6 theta. That's from negative pi over 6 to pi over 6. Okay, so that equals 9 over 4. If you plug in our pi over 6 plus, actually if you plug in pi over 6, that gives you sine of pi, which is 0, so we can just leave that, minus, you plug in negative pi over 6, so minus negative pi over 6, plug in negative pi over 6, that gives you negative pi, which sine of that is just 0, so we can leave that. So we have 9 over 4 times 2 pi over 6. That actually simplifies to be 3 pi over 4. Okay, now this is just the area of one petal. Remember that. Area of one petal. So to find the area of the entire graph, we just have to multiply that by 3. Area of all petals, that's just 3 times 3 pi over 4, which is 9 pi over 4. Okay, so that's our overall answer there. Alright, so hopefully this made sense, and I will see you on the next video.